All right, I'm very excited to be here with John Platt. John, tell us a little bit about you and your background at Microsoft Research.
Well, I'm a distinguished scientist here at MSR, and I've been at Microsoft for 17 years, and I've worked on both machine learning and other things like computer vision and computer graphics and signal processing and audio. So I like a lot of different fields of computer science, and so I've been working both pushing state of the art in terms of the research and also getting this research into our products.
And how did you get started in the field of AI?
Oh gosh, I've been working in AI and machine learning for about 32 years now. I got into it in 1982 because at Caltech at the time, I was living in Southern California, and John Hopfield and Carver Mead were there, and they were starting to they wanted to build chips that sort of acted like the human brain, and that was so exciting to me, I decided to go to Caltech.
And I always ask people, what was your first computer?
Oh, let's see. I first programmed a computer in 1973, and that was with a language called PL1, and I think it was a cyber computer. It was at the University of Chicago.
Nice. And so how do you define artificial intelligence and machine learning as well? Are they two sides of the same coin, or how are they different?
Oh, okay. They are very intertwined. So I would define artificial intelligence as software that's trying to emulate the human mind. So that's often specific to a domain, like computers that can see, that's computer vision, or computers that can listen, which is like speech recognition, or computers that can read text, which would be natural language processing or text mining. So that's AI, emulating the human mind. And then there's a set of specific techniques, which are machine learning. In machine learning, it's a set of techniques that turns a data set into a set of software. So it's sort of an alternative way of programming. So instead of writing a specification and then trying to sort of hand build a piece of software that matches the specification, instead you have a data set and perhaps some desired output or behaviors that you would like when you see elements of that data set, and machine learning will generate a piece of software that will match your goals on that data set.
Before we got started, we had an interesting discussion about AI. Tell us a little bit about how AI has changed over the decades, and I was surprised to hear how far back it goes.
Oh, sure. AI is really intertwined with the history of computer science. Some of the original computer scientists, I think, were interested in computers because they wanted to build artificial intelligence or artificial minds, going back to Alan Turing, who proposed the Turing test. AI dates back to for example, to the 50s. One of the things I told you about before was people might not realize, but there's a little adaptive one-layer neural network in pretty much every phone. What it does, it performs what they call acoustic echo cancellation, so that when you speak into the microphone, it doesn't cycle, or when you get the sound out of the speaker, it doesn't go back into the microphone and echo and make a screech. You sometimes hear that when it fails, but the fact that that you don't hear that a lot, that's actually a little algorithm that was built in 1960 that was one of the original AI algorithms by Bernie Widrow. So it just shows you that sort of AI and machine learning has been around for many decades, and it's ubiquitous around us. You might not even realize it.
And what is deep learning compared to traditional machine learning?
Okay, deep learning is a particular kind of machine learning, and it addresses a famous problem in machine learning called the problem of representation. You see, many of these problems become relatively easy. For example, let's say computer vision, if you just had the right representation. One pixel in an image tells you very, very, very little about what's in an image. If I just took one pixel of a picture of your face, it would be very difficult to tell what that was. But if you transform the data and transform it enough times, then you can get a very high-level representation. For example, it might be, this is a face of someone with brown hair or with blue eyes, and then I could recognize who that was given the high-level features. Now, previously, before deep learning, people would hand design or hand engineer the mapping from raw inputs like pixels to features they could use, and then those features would be fed to a standard machine learning algorithm. The recent success of deep learning shows that you don't have to hand engineer, that in fact computers are actually better at engineering those features than people are. So what you do is you take very large data sets and you learn how to transform the raw data like pixels into high-level representations. Another nice thing about that is that the reason why it's called deep learning is that it does it through successive layers of transformation. So it goes from a low-level representation like pixels to edges to textures and whatnot. And that sort of emulates the way the brain is architected, that your brain itself, like in your visual system, is structured in layers. And as far as neurophysiologists know, that each layer is computing a more complex function given the inputs from the previous layer. Deep learning does the same thing. That's why it's called deep.
And how much of this is defined by the programmer compared to what the machine picks up over time? I mean, does the programmer go to the specificity of, like, these are the edges, these are the features to look for, or does the device discern that over time from looking at a bunch of different pictures, for instance?
The device discerns that over time. That the nice thing is, like, the programmer might say, you know, I want 6 steps of transformation, I want 6 layers. And you might specify, well, how many features do I want? Do I want 1,000 or 100, maybe depending on how much compute budget you have. And then you turn it loose with a data set, and it will actually figure out, oh, I want to do edges, and I want to do this kind of filter or that kind of filter. So it figures it out. In fact, you often can't tell, is it really computing an edge, or is it doing something more clever?
And why would a developer use one approach as opposed to another? What are the differences in application between deep learning and machine learning?
So deep learning you would use when you don't know how to hand transform the raw data into a data set that you like. So for example, one example I give is, let's say, doing movie recommendations. You know, mostly you know what the representation of a movie is. Who is the director, who starred in it, which users liked it, or maybe you want the demographics of the users. It's fairly clear how to encode that into software. But for images, or for sounds, or for text in general, it's very difficult for an engineer to know, oh, how am I going to represent these pixels? In fact, that's been the major problem in computer vision for many decades. So now you would use deep learning to essentially develop representations for you that you could reuse on multiple tasks.
So vision is one input method. It's one sense for humans, but we have many senses that we depend on. Is it the same for machines?
Well, just starting to be. I mean, many of these fields of AI, each sense, so to speak, was an individual subfield. Like there were the computer vision people who just studied pixels, and there was the speech recognition people who just studied speech. But when you think about how human brains learn, like when little kids learn, they use all the senses they have available to them. They read, they hear, they see if they can. And that's, in fact, there isn't a supervision signal. It's not like people tell them usually, oh, this is a Coke can. It's that they learn from experience. So we're starting to see more and more of that. There's a lot of multimodal learning that people are starting to do with deep learning, like trying to correlate images with text or text with sound. And that's terribly exciting because you might be able to learn very sophisticated things from the intersection between 2 modes.
Can you share some examples of where Microsoft's work in these areas have made its way into projects or products?
Sure. In terms of products, we're very proud of the fact that we were the first company to develop a large vocabulary speech recognition based on deep learning, and in fact that has gone into our speech recognition products. For example, on our search engine. Also in our search engine, we use deep learning to kind of analyze images, and so that's also part of the search engine. So that's very exciting. And we're doing a lot of research currently into different ways of applying deep learning to various interesting tasks. So that's still an area of active research, especially around the 3 I mentioned of artificial intelligence, images, audio, and text are all very interesting for deep learning.
And how is something like Cortana different from a search engine?
That's very interesting. Cortana is just great. I think it's one of the most fun things to work on. Cortana is what they call a dialogue system, which is actually tough. It actually responds to you. In a search engine, you just give a short query, maybe a couple of words. But in Cortana, you actually speak to Cortana, and you expect that Cortana will actually say the right thing back to you. And if Cortana is confused, she'll ask you for clarifications. even though it seems very simple and obvious, it actually turns out to be an incredibly tricky problem of how to make that work well and robustly about anything. So that's still, we've got enough to ship to our customers and make them happy, but it's still an open research problem that we're all super excited about.
It's interesting. It makes me wonder, should search engines ask for more clarification if they don't understand something?
Sure, I mean, to some extent, Cortana has a search engine inside of it, so it would be really neat if there was ambiguity, or if Cortana wanted, if you were unhappy with your search results, maybe you could ask Cortana for more. So yes, I think that's actually the future, is to have a dialogue system sort of handling a lot of your information needs.
And how should developers think about deep learning? What are the applications, and at what point should they start considering it for their projects?
Well, as I was saying, you decide to use deep learning and try to train up something, but it takes a very large amount of data and compute. Certainly, you could do that in the cloud on Azure. But it could be that if they think, oh, I have a scenario where I would love to have a computer that can, I'll point a camera at something and I want it to recognize, or I can listen to some sound and have it make a decision, or I want it to process some text and do something intelligent. If that's one of the scenarios, then what I would recommend is using, if you can find a pre-defined deep learned feature extractor, and then build something on top of that. So for example, that in the Cloud ML, Azure ML product, you could be able to use a module that has already been pre-trained with deep learning, and then use Azure ML to build a specific classifier on top of it.
How does a developer become an expert in this space?
Well, the way to become an expert in neural networks or machine learning is to try and just to keep experimenting for perhaps thousands of hours. A lot of people at Microsoft, because we have so much data and we have so many different scenarios around the company, many of us have just spent months or years applying machine learning to various tasks, and that's how you learn. But now that we have the tools that are in Azure ML, other people can start to accumulate this experience too, and so they should go ahead and try it on their own data. That's how we did it.
Yeah. What's an example of some of the most advanced AI that Microsoft has?
Well, I would say that the Bing search engine is probably the most advanced a collection of AI or machine learning that we have. And when you think about it, a search engine itself is sort of artificially intelligent. It really has to know what you mean by the short queries that you give, and has to sort of understand all the documents on the web. So the way we built Bing was out of many, many pieces, each of which was trained with machine learning. So I would say that's probably the most sophisticated one that we have at Microsoft.
In the past with search engines, it was effective to just search for the keywords you thought would show up on a page. We're at the point now, do you believe, that you can just use a natural search term?
There are examples in our products which prompt you with natural search terms. If you look, for example, at the Power BI product, you can actually use natural language to sort of navigate through your system and get good visualizations that you want. So yeah, getting natural queries against data sets is definitely happening now.
Can you talk a little bit about Project Atom and what makes it unique?
Oh yeah, Project Atom was very fun to work on. I helped Trishul Chilimbi a little bit. Project Atom is a distributed system that allows you to train very, very large-scale neural networks. It's unique because a lot of people have been getting away from the use of sort of standard CPUs to do deep learning, training of deep learned models. But of course you get a lot of elasticity. You get, if you can use the cloud to train deep learning, you can then get vast resources available applied to it. Unfortunately, the reason why people have been moving towards GPUs is because per node they're so much more effective. But what Trishul did was very clever in that he figured out a way of sort of effectively marshaling many, many CPUs all to work on the same neural network. And that's actually pretty tricky. I mean, one of the hardest things about a distributed systems is figuring out how to actually effectively use a large-scale computational infrastructure. It's very easy to build something with thousands of nodes but waste most of the capacity of them, and Trishul doesn't do that. So that's very exciting, and now that really opens up. I mean, Trishul and I are speculating about what kind of amazing things we can build with Project Atom. I mean, what kind of large-scale systems can we build, and how much more amazing sort of AI stuff can we do? So I'm very excited.
So talk about some of the capabilities of Project Atom.
Well, one of the most exciting capabilities of Project Atom is in computer vision, or recognizing objects in an image. Trishul trained it up to recognize 22,000 different categories of images, and these are very fine distinctions. I was very excited to see you could tell the difference between a emperor penguin and a king penguin. I don't think I could tell the difference. And it's not perfect, but it's really remarkably good. It's substantially better than existing systems that have been published, and it's just incredibly fun to play with. You could feed it images. One of our directors fed it an image of a rabbit running in its backyard, and it said rabbit. So that was terribly exciting. Anyway, so it does very, very good whole image vision recognition.
I've often wanted to get two Windows phones and try to get Cortana to have a discussion with itself. Are there any examples you've seen where two AIs have a discussion? What does that look like?
Well, I don't know if I'd call them AI, but inside of the editor called Emacs, there are two chatbots. One of them, which is Eliza, which is the classic psychoanalysis one, and one of which emulates what Zippy the Pinhead, the comic book character, says. Yeah. So there's a command to have them talk to each other, and it's quite surreal. Poor Eliza tries to psychoanalyze Zippy, who is just saying random things. It's quite amusing.